Welcome back to WAPSI. So we can go to another section of magnetostatics. The first question is, a strong magnetic field is applied on a stationary electron. Okay, the electron is stationary. Then the electron moves. All options are related to some kind of motion. And in option C, remain stationary, and option D, start spinning. Okay, so three options are related to a motion and one options are related to a stationary position. Okay, if it is moving, then we want to calculate the direction also. So a stationary charge want to move, then there should be a force. Okay, so which is the equation for the force? We know the equation for the force by the Lorentz equation. F is equal to Q into E plus V cross B, and B is the magnetic field that is given and E is the electric field. Okay, so a strong magnetic field is applied, so that means the B is in here. Yes, B is here, and a charge is placed, that means there is electric field. Okay, but there is no there is no charge is introducing to there, so the force by the electric field is not in here actually. So for a electric field produced by the charge is there. Okay, but there is no other charge placed in that, so we can neglect or we can avoid the force component of force due to the electric field. Next one is the component of the force due to the magnetic field. But see, here we have a charge, but we want a force due to the V cross B. That means the velocity of the charged particle should act with the magnitude of the magnetic field. So there is no velocity actually here. So the F is net force is 0. Okay, because the velocity is 0 in here. If there is a velocity, then we want to take the cross product with the velocity with the magnetic field. So here the force is 0. So it's remain stationary. Okay, so we can move to the second question. Okay, two parallel wires in free space are 10 centimeter apart. Okay, two parallel wires with 10 centimeter apart, and each carries a current of 10 ampere. Okay, here 10 ampere, here 10 ampere. In the same direction, the force exerted by one wire on the other. Okay, we want the force, the magnitude of the force, and can we do we want the direction of the force? Yes, because read the options: attractive, repulsive. So the two current are in the same direction. Each carries current in 10 ampere in the same direction. The same direction means the force is attractive. Okay, so this option C and option D can be neglected. Okay, so then we want to find the magnitude of the force. Force per unit length is given by the equation mu 0 I1 I2 all divided by 2 pi r. Correct? Yes. So mu 0 is 4 pi into 10 raised to minus 7 multiplied by the current I1. I1 is 10 and I2 is 10. So 100 divided by 2 pi into r. What is the distance between? 10 centimeter. Change that to the standard unit, that means meter. 10 centimeter is 0.1 meter. So 0.1. So 4 pi by 2 pi is 2. 2 into 100 is 200. 200 by 0.1 into 10 raised to minus 7. Therefore, the force per unit length is equal to 2000 into 10 raised to minus 7, which is equal to 2 into 10 raised to minus 4. Okay, and Newton per meter. Okay, so the unit for the force is Newton, unit for the length is meter. So Newton per meter is the magnitude of our force per length is 2 into 10 raised to minus 4. Okay, so 2 into 10 raised to minus 4 attractive, which is option A, is the correct answer. Okay, then we can move to the third question. Okay, a toroid with a thick winding of n turns. Okay, so we have a toroid. This is, consider that this is our toroid. Okay, with the inner radius and a outer radius. Okay, inner radius r1, so this is r1 and this is r2. If it carries a certain current I, the variation of the magnetic field due to the toroid with the radial distance is correctly graphed in. So we want to observe each graph. See, the first one shows the magnetic field, high magnetic field for the R1, and they have given the equation mu 0 Ni by 2R. Since R1 is, see, the outer radius R1, okay, this outer radius R1 and the inner radius is R2, that means R1 is greater, that means R1 is greater than R2. So how we get a maximum value for R1? And the similar condition in here, the denominator is R1 and that is greater, and how then we get the maximum value of magnetic field? By logically the maximum value is given to R2 because R1 is the outer radius, R1 is greater than R2. Okay, so this option A is incorrect and option B is incorrect. And yes, by logically R1 is greater and R1 is greater. Okay, so logically this is correct, R1 is less, and yes, and R2 is comparatively less, so R2 gives 1 by R2 gives comparatively high. Okay, but in this graph it is saying that, it says that the magnetic field increase when we go from where R1 to R2. That means R1 is the outer radius, that means when we are coming from this point to this point, the magnetic field is increasing, but that is incorrect. Magnetic field inside R2, that means the magnetic field less than R2 is 0, that means inside there is no magnetic field, and inside the toroid the magnetic field is a constant. Okay, this is the main concept in here, the inside the toroid the magnetic field is constant. Okay, focus on this point, and this is the equation. Okay, and this is the equation to calculate the magnetic field inside a toroid. Okay, so we can move to the fourth question. A tightly wound long solenoid has n turns. Okay, n turns per unit length, that's why it is represented by small letter n. A radius r, small r, and carries a current I. A particle having charge q and mass m is projected from a point on the axis. So first I will draw a solenoid. Consider that this is a solenoid, okay, with a radius r and carrying current I. A particle having charge q and mass m is projected from a point on the axis. Okay, so this will be the axis and this is the point on the axis. Okay, in a direction perpendicular to the axis, so it is projected perpendicularly. Okay, the maximum speed of the particle, yes, the velocity is acting towards it and the magnetic field is acting towards it. So by Lorentz force, F is q into v cross b. Okay, that means the mutually perpendicular direction, so a force will acting towards it. So this, due to this force, it will bend its direction and the charge will flow like this. Okay, helical path. Okay, due to the force, due to the cross product of velocity and the magnetic field. Magnetic field is in this direction and velocity in this direction. Okay, if the magnetic field is in direction, then it will just retrace the path to the opposite direction. That means like this. Okay, So we want to calculate the speed, velocity. So inside, when we are a magnetic field is applying to a projected charge is nothing but V is equal to BQR by 2m. Okay, this equation we already studied this equation from the chapter of the D's. Okay, that means oscillator using the D's. Okay, so but this equation is not given. Then see, mu 0 is in the option, so we want to substitute the magnetic field inside a solenoid. The magnetic field inside a solenoid is mu 0 Ni. Simple. N is the number of turns per unit length and I is the current. So using this, V is equal to mu 0 Ni into R by 2m. Okay, which option? Mu 0 Ni. Sorry, charge. We forgot to write the charge. So Q is there. Mu 0 NiQR. Mu 0 NiQR by 2m. 8m, 4m. So these are wrong. Here m, these are wrong. Option B is the correct answer. Mu 0 NiQR by 2m. Okay, so we can move to the next question. Okay, earth magnetic field. Next question is related to earth magnetic field. Has a horizontal component except at. Okay, so I will draw. This is our earth and this is our magnetic field. Okay, see, in this direction it has both vertical and horizontal component. In here there is only horizontal component, no vertical component. Vertical component is absent at equator. But the question is, horizontal component is except at. Okay, where does the horizontal component is getting 0? See, in here the magnetic field is directed towards the horizontal. There is towards the vertical, and there is no horizontal direction. So at the magnetic poles there is no horizontal component, only a vertical component. But in equator there is only horizontal component, there is no vertical component. Okay, so in this question option B is the correct answer. Okay, so we can move to the next question. Which of the field pattern given below is valid for electric field as well as for magnetic field? Okay, see, I already said to you the right hand thumb rule. Okay, place our hand like this or this. If this is the direction of current, okay, if this is the direction of current, this can be the direction of magnetic field, curling magnetic field. Okay, and inside the solenoid the magnetic field is in a straight line. Okay, then there will be a current. Okay, if this is the direction of magnetic field, this curling will be the direction of current. So this kind of curling, see, this kind of curling is valid for both the magnetic and magnetic field and current. Which pattern gives you the valid for electric field as well as magnetic field? So option C is the correct answer. Okay, and we can go to the next question. Okay, the current following through an inductance coil of self-inductance. Self-inductance is 6 milli. That means 6 into 10 raised to minus 3 Henry. Okay, at a different time instant is shown in figure, as shown. Okay, the EMF induced between time, they have given a time as 20 seconds to 40 seconds. Okay, so this is the portion. Okay, this is the portion, and we can, in this time interval, we can find the rate of change of current with respect to rate of change of time. Di by dt is the slope, which is equal to negative, because it is pointing downward. So the negative change in current is its unit is 2, so the half of the unit is 1. So 4 the final point is 3. Okay, the initial point is 4, that's why I put a negative. 4 minus 3 is 1, by dt is 40 minus 20 is 20. Okay, so minus 1 by 20 is the di by dt, and we know that EMF is equal to minus L di by dt. Okay, L is what? 6 millihenry, which is equal to 6 into 10 raised to minus 3 is multiplied by negative, and this negative can be cancelled. So di by dt is by 20. Okay, so which is equal to 6 by 2 is 3 into 10 raised to minus 4. Okay, so 3 into 10 raised to minus 4, option B is the correct answer. 3 into 10 raised to minus 4. Okay, so we want to use some kind of mathematical equation in physics. Okay, like this slope, that means the slope and the derivative both are same. The concept behind the slope and the first derivative are same. Okay, okay, this one is the very important. This question has very importance in exam point of view, because this question comprises some 2-3 formulas. Okay, I will say to you. The magnetic field at the center. Oh, we have to find the magnetic field at the center. So by how many source do we get a magnetic field in here? Here is a circle. Okay, so and O is the center of the circle. So some magnetic field can be contributed by the circular shape, and here is a line. Okay, so magnetic field can be caused by a line. Here is the another line. Okay, so here is the another line. So some magnetic field caused by, say, the line. Okay, so I will explain to you. The magnetic field by a circle is nothing but mu 0 I by 2r. Okay, in here the circle is not completed, only 270 degree, that means 3/4 of a circle is given. So 3/4 of magnetic field of a circle is necessary. So 3 mu 0 I by 8r is contributed by the circle. So this option can be incorrect, and A and B are incorrect. Option C and D can be the correct one. Okay, in addition to that, this can be a magnetic field. Okay, so this is revolving, the current is revolving in a clockwise direction in here. So the magnetic field should be into the page by right hand thumb rule. If place our fingers in the direction of clockwise. Okay, so the thumb is pointing towards the page, so inside the page the direction is into the page. Okay, and see the in here the current is looking like a straight line, so we can make our thumb is in the direction of the current, and see the hands are my fingers are curling into the page. Yes, into the page. So the current or the magnetic field contributed by this line is also same direction with the initial direction. So there is no negative will come. Okay, only positive will come. So this is the logical method, and I will explain to you the theoretical method also. Okay, and this is the equation. If this is a straight line and we have to find a magnetic field B at a distance r from the straight line. Okay, and they have given the theta 1 and theta 2, then the magnetic field is mu 0 I by 4 pi r is multiplied by cos theta 1 plus cos theta 2. Okay, if this cos theta 1 is 90 degree, then it will become sin theta 1. Okay, it is not cos, it is sin. Both are sin. Okay, if theta 1 is 90 degree, then it will be maximum. So it is if this line is infinite line, then theta 1 become 90 and theta 2 become 90. So Sin 90 plus sin 90 is 2. So 2 into 2 pi 2 into mu 0 I by 4 pi r gives mu 0 I by 2 pi r is the given equation from a infinite line. Okay, and in here, see, in here this line is coming from infinity, so this angle can be treated as 90, and this line is stopped at this position. Okay, so the magnetic field at the end of a line is what? Sin 90 is 1, so that's why we get the magnetic field at the end of a line is as mu 0 I by 4 pi r. Okay, so just add the magnetic field due to a infinite line at one of its end is mu 0 I by 4 pi r. Just add it. So option C is the correct answer, and you have to study this equation. You can substitute. So if the structure is like this equilateral triangle, you can substitute theta say 60, and if the line is coming like this, okay, this is the structure and following a circle, okay, following a circle, then you can easily derive the what? The magnetic field contributed by this part. Okay, this will be 30 and this will be 30. Sin 30 is 1 by 2. 1 by 2 plus 1 by 2 is 1. Okay, so using that kind of mathematics, you can easily derive the magnetic field. Okay, so this one, option C, is the correct answer. Okay, bye, see you later, and signing off. My name is Justin Joshi. I am signing off. Okay, bye.